So yeah, welcome everyone. This is fun with Lambdas talk. Just out of curiosity, the whole Mixpanel is trying to go through these chapters of the new book that Scott Myers came out with. Who has done their homework and has read all four whatever chapters, mini chapters from the book? Done your homework before coming here? No problem. A few hands went up, but anyway, you're not going to need it at all. So don't worry about it if you have not gone through it. And if you are, new to Lambdas, that's fine too. Plan to go through the basics of Lambdas at the beginning and later rather interesting examples. So really quickly, my background in functional programming. I mean, this is probably not a surprise for you guys. It's Lambdas. It's all about functional programming, and whether you like it or not, if you are using Lambdas, you are doing functional programming in some sense. My work in this many years ago in Lisa, and then more recently in C# RX actually. That's one of those libraries I'm really into these days. Reflex, C++, and perhaps you have stumbled upon some incorrect blog posts on C++ truths. I apologize if the programs no longer compile, or there are better ways to do the same thing. So and that's the likelihood increases over here. So I mean, you may find some useful bits over there. So yeah, coming back to functional programming, I mean, why should we care about functional programming? It is really out there. I mean, this talk is not going to be why functional programming and what's good is bringing to you, or to software development and whatnot. Professional software developers like you and I are paying big bucks, sending several people to whole bunch of conferences like this. And it has really caught on. I mean, I'm pretty sure this is not the whole list, and perhaps in San Francisco Bay Area and San Francisco specifically, there are several. There is one, I think Scala Days is this Friday, or maybe I don't know, end of this weekend, something like that. Lot of stuff, functional program stuff is going on, and that's why I got interested in what is this thing, right? I mean, why are people so interested and gung ho about it, and what is it going to bring to the table? But of course, this talk is not about why functional programming. You will find plenty of good text, online, blog posts, books on it. So I'm going to skip all that and simply jump to what does it mean, to have Lambdas in C++, because that's the one of the ways now you can do functional programming in C++. So let's jump right into it. We'll go through a lot of examples. So here is perhaps the first one. But okay, so those who have not heard lambda expressions at all before, here is the definition for you. The definition really doesn't do a whole lot of justice unless you see a few examples. So it constructs a closure. And it's like, wow, what does that mean? That was my expression, at the beginning. What is this closure thing? It's an unnamed function object. Function object, I think that sounds a bit familiar. It's an object, so that's a good indication. Function object, perhaps you have heard about that because that's a pretty old terminology in C++ world. It's capable of capturing variables in scope, and I think that's the single most important capability of a lambda and a closure it produces. So I really like, so you will find some texts which say, well, lambdas are anonymous functions, and I don't quite prefer that terminology, anonymous functions, because in fact that's how I read about them at the very, very beginning, like before even C++ had lambdas. Like anonymous function, okay, a function is a function, and then you don't generally associate state with a function, at least in C++. Okay, there can be free functions, global functions, and you just call them. There could be static, but that's not what we are talking about here. So, but when we think of closures as a function object, that immediately gives an important clue that it's an object, and which means it has got some state. Potentially, it has got some state. And I think that is very important to so this is a good definition, I think. But what does it really mean to like create an object? I mean, there are so many other ways to create objects, and why is this way special? That's the later part of it. It's able to capture things in your environment, and that's pretty good. So here's an example. So absolute sort, it takes really trivial array of floats as input, and it just sorts them in place. This is standard stud library, stud sort. We know the size of it, and that's why this is the beginning of the array, and the size of the array here. Those are the first and second parameters are essentially the bounds of the array, and what you see on the next line here is essentially a C++ lambda expression. The way to parse it is really, let's not look at this square bracket just yet. The rest of it should look very much like a function, and it is in fact a function. I'll be a little more intelligent than other functions that you see in C++. So it takes two arguments, two floats A and B, and we are simply calling absolute on both and returning the comparison. So this particular lambda expression produces a object that is passed as the third argument to stud sort, and that's about it. It's really nothing fancy. You could have created this. In fact, we'll look at an example. You could have created this outside this function and passed an object, instantiated manually. You could have passed it, and sort we just happily use this closure and object to compare the array that we have given. Obviously, the end of absolute sort, you're going to have a sorted array using this functionality. The thing here is, you can see not the logic, but the predicate, which means really the condition on which it is going to sort, right? It is as long as A and B, A is less than B, it's gonna shuffle them or whatnot. It's going to do its thing. So you can see the code right here. Without lambdas, what will happen? You will probably move this code outside somewhere else, in global scope or whatever, and then use a reference. So you will use a name. You will give a name to it, and you will use that name over here. But you don't have to do that. Lambdas essentially take that pain away. You don't have to name things. That's why it's anonymous, and it's a function which doesn't have any name, and compiler does the right thing for it. Any questions on this so far for those who are really new to lambdas? Right? Feel free to stop me, anytime. This is meant to be really interactive presentation. Later on we'll see several examples, and really I'm going to give some time to really think about it, and let's have interactions about some code examples later. Okay. So now the intent of next few slides is to really show you that it is a classic function object. There is nothing that exists at runtime because of lambdas that you don't know already. If you know C++ objects, constructors, and function call operators, you know everything that exists at runtime when a C++ lambda is used. So here is good old C++, class comparator or whatever has a little bit of state and a constructor and a function called compare. It takes just one argument. We changed from the earlier example. It's no longer taking two arguments, taking just one, and it will return a boolean based on how A compares with B, and depending upon A is going to be the same always for a specific object. So here is an object called f, more like a, because we are going to call it using, we'll later replace this with an operator. It's more like a function. So when you run this, instead of me talking about and explaining this code, I think I'll just let you look at it for a second. You will get it. It's pretty straightforward and simple code. It's expected to print true or false depending upon 3. Like for 0, 1, and 2, it's going to print false, and for others, no, for 0, 1, 2, anyway, it's going to print true, and for others, it's going to print false. That's it. It's very trivial. Let's see if we can. Was there a question? No. Okay. Yeah. So let's go ahead and try to see if we can replace this with a progressively with a lambda. So instead of compare, I replace that with a operator bracket here, which is essentially a function called operator, and that's the only change I did. Now we do no longer have this compare function. We just replace that with that, so that's your new syntax now to call the same function. It's essentially, you just name the whole thing differently. That's it. Let's get rid of the class name itself. So this is some pseudo code, not via C++, of course. The compiler generates these hashes for us. It's essential. Eventually, we'll replace this line as well with a lambda, and it will come up with its own name for this class, which will look very similar to this. It will have a constructor and this, but of course you won't be able to see that because the compiler will do just the right things. When you pass an argument, it will capture it and so on and so forth. But essentially, it will produce code that will do this thing, which being the constructor and creating some state for you and then assigning it, those kind of things. So let me show you the code itself. So let's try through that. And this piece here, this rectangle over here, it is essentially equivalent to that code here. It has got no name, it has a type, but you can ask for the type, but you should not need it. It's unusual and weird to ask for the type of a lambda. That's not typically required. So when the compiler looks at this expression, it basically produces that. And because we really don't know the type of this, we are going to use auto. Now, are people familiar here with auto? Auto is just that's good. Just a way to whatever type is on the right hand side, I'm of that type. So F is that, and the rest of the code stays the same. You could just call item, and that's it. So now you can see that this particular operator, this whole body got moved here, and the return type. The one important thing here is the lambda, you did not specify the return type. The compiler is smart enough to identify that, to figure that out, deduce, that's probably the correct term here, looking at whatever you're returning. And there are ways to specify return types as well, but let's not go into those syntactic things just yet. Any questions on this transformation? Like how lambdas get essentially turned into a class with some state depending upon how you use it. All right. So let's do a quick recap. They are anonymous functions. When they don't have any state, it's just like a function. In fact, compiler, I think, guarantees that it is going to be a function, just like a regular function. It is written exactly in the place where it's needed. Just like we used earlier, or in sort. You don't have to declare it, up above and headers and C++, CPP files and whatnot. Just use it right where it's needed, and that's really powerful. It can access variables available in the scope. We look at some examples of that, which is the most powerful capability of a closure of a lambda. May contain state. Yes, it's called a function object. That's why it's called. You may have some state, and just like an object. The next two things are really what, and perhaps the third one here. It can be passed to a function. We already saw that. Absolute sort. You just pass an instance of it, a closure to the sort function. So it's like it helps to think about, hey, I'm just kind of passing this functionality, a behavior through arguments instead of a value like a vector or 10 or I don't know a list. I'm passing in behavior itself, a function, and that thinking is as you get into lambdas and more into functional programming, it becomes sort of second nature, right? And it really helps. So passing functionality and returning from them, it's quite intriguing when you start returning lambdas. What does it really mean? You're basically creating functions on the fly. Like for the first time around you got a function and it's like does something. Second time around something else. We'll see examples of that. These two are really the game changer in lambdas and in C++ because of lambdas. We looked at return type is reduced automatically, and in C++14, which most I think compilers, at least good compilers, have support for this. We don't even have to specify a type of B here. In earlier example we said float. In C++11 you'll have to say that, but here in C++14 you can opt out and just say, hey, auto, I don't know what it is. It can be anything, whatever is used at the call site. Whenever you use this, see if you can deduce it. Yes, it will deduce it, and of course the expression should make sense for that type. This won't make sense for a vector or some crazy type, but would make sense for primitive types. So that's auto. This is specifically C++14, and it essentially maps to a template version of operator, function call operator. Those are the mechanics. We don't have to go into details of that just now. Okay, any questions on these capabilities? Want me to explain anything more? What do you have to do? Okay, so rest of the talk is actually, I want to thank, who knows who this guy is? Right? I think you have seen this talk before.
I've seen part of it, yes.
Yes, so
I have no
if I may,
anyway.
okay, go ahead.
Well, Douglas Carter.
That's right. He is, he has spoken several times at the Silicon Valley Code Camp, and the session he gets is like a huge auditorium. It's like 400 people attend every year. Pretty amazing talk in JavaScript, and the following talk is really an adaptation of that C++ spin to it. It's amazing that you can write nearly exactly same code in C++ that you can write in JavaScript. It's really weird. All right. So let lambdas begin. May the fun be ever on your side. I can never say that sentence in one breath. It just never happens. So, all right. So here is and now audience participation. Okay. I really need your help to go through these questions. Sort of really simple. Probably no more than 5 lines of code in each problem, really, right? And let's go through those. So we want to write an identity function that takes a single argument and returns the same argument. Like how dumb and trivial can it be? So, but let's start there. So identity 3 should return 3 essentially. When you start with an answer here, it's pretty simple. Perhaps you already anticipate what it's going to look like. Auto identity, a lambda x, some x, I don't know what x, some x, could be anything depending upon how it is used. So identity doesn't really say which type it's going to return, it's just anything that you pass in. So makes sense so far? You can can create a lambda and assign it to this object. So this identity becomes the instance, and that's it. No state here, just function.
I would like to point out that we've already got a confusing bit of syntax on this slide.
This slide or the
yeah,
slide before?
In that you've got auto identity equals auto x, and you would kind of look at that and say, oh, okay, auto, and it returns auto, I get it. But it doesn't return auto.
It does not return auto. What do you mean by that?
Right. Auto identity, that first auto on the line there is saying deduce the type of identity as a lambda type. It has no relation to the return type of the actual
Yes. Yes, that's a good point. It is very important to know that identity has nothing to do with x. Well, it's going to return x, But when the compiler goes through this, return x is not executed. It says, hey, there is a function. Let me make a function for this code here, and I'm gonna name it identity, and that's it. It's an assignment. It's not a return. So, yeah, that's a good point. And yeah, go ahead, question.
Maybe I'll cover this later, but before I forget, so like, what would that type end up looking like for identity? Let's say, what if I wanted to specify the return type, as a check for myself?
Specify this x return type. Return
Yeah.
type of x.
Yeah, and so how would I write the
There
first
is
auto?
syntax to do that. I think generally what you do is write between these two, right after the closing parenthesis, you will write arrow and a type.
I see.
Let's say an int and then arrow int, and then the issue is it can return only that type.
Okay.
So it's just like a function, right? So as long as you are using anything that's convertible to integer, it will work. But then maybe for other types, it's not one.
And
So
if you want it to remain anonymous or remain generic, then you could it would
That's
be
it.
arrow decal type of x.
yeah, yeah, that's the syntax. That's a very non-generic sort of return type, or you can use that. Which in this specific case you don't need it, because compiler is smart enough to just look at x and see, hey, you're returning x, okay, whatever x will be used at the call side, that's your return type, and that's it. The compiler will figure that out. We're not going to use any return type ever, in this talk at all, actually. Just not, because we're going to soon start returning lambdas, and you cannot really say what the type is. You just have to leave it to compile. Okay? So write three functions: add, subtract, and multiply, that take two parameters each and return their sum, difference, and product. Again, very basic 101 kind of question. Just giving you a feel for the syntax for lambdas and autos particularly. So if you are comfortable with this, let's not forget again, we can still define functions the old way, right? This is still valid. Of course, it makes sense only for integers. This is a little more general, but you could see how they are related.
Can you use auto as a lambda parameter type?
In C++ 14, yes.
Okay, it's new in 14?
Yes.
Okay.
Can you use auto as a regular function parameter type?
I think so.
I think not, or I think not until maybe 17 it's coming.
Oh, really?
But I think template is, you said say template.
Oh, okay. I think you can do it for return types though.
Oh, yes.
Yeah, that's
That's
since
11.
11. Yeah. Yeah.
How many
Makes
people are
sense to
using
support
C++
auto.
14 compatible compiler?
Oh. Hi, can I be your friend?
It's taken some doing. We only finally switched to it about a month ago.
Which one are you using? Are you using client or server?
We use Clang and GCC 4.9, depending on the platform.
So you're not using Microsoft?
So with the,
Yeah, we're waiting for the.
Yeah.
like with the add function, could I call that with like have two different calls to it that has different types of?
Much
Yes.
like 14, not
Okay.
Yeah. Because the way it works is, for this particular lambda, it turns into essentially a compiler generated class that has a template function called operator parenthesis, and it's gonna have some t, and that t and u actually two different types, tx and uy, and you could pass two different types actually if you want. Of course, this expression should make sense for those. That's a different story, but that's how it essentially maps to. Yeah. Same for subtract here. Yeah. Okay. All right. now this is going to get a little more interesting slowly. So we need a function called identity f that takes an argument and returns a callable. It is slightly different from the earlier identity function. It is identity f because it returns a callable that returns an argument. So now maybe I should, perhaps, before we start cursing here, say what's the point of doing all this? There is a maybe I skipped that earlier. I should have said it earlier. So functional program, right? There is a good chance, hopefully, by the end of this talk, you might be able to read a tiny bit of Haskell code. Yeah, just a tiny bit of Haskell. And if you could do that, I think then I would think I have succeeded. And I'm going to have a little bit of a code snippet at the end to give you a feeling for it, but it's about functional programming. I mean, there is no higher aspiration than Haskell, right? In functional programming, maybe there are. It's like other functional languages are beyond Haskell. Apparently, those things exist, but the point of going through this is, really grok at why is it, what is this Haskell thing, and perhaps understand the very, very basics of it. Mind you, by the way, I mean, if you drink that Kool-Aid and go further down, sufficiently further down in Haskell route, taking that route, there may be some point where there is no point of return, because you will get sucked into this, under event horizon, and there is no point, there is no possibility of escaping, and you will hate the programming you do nowadays. It's like, did I actually do that? It's like whatever years ago, and how do I even survive doing that? I mean, I'm barely starting to read Haskell, but there is some, okay, you'll find ton of material on that. It's like, hey, this is the way. This is like more rigorous computer science, and it's fun. It's not, if nothing else, it's a lot of fun. I can assure you that. If you find this rest of the talk fun, you'll find Haskell really good. Okay, so enough of that. And okay, identity f, we want to return something, a callable, could be a class or whatever. And when that is called, it essentially returns 5. IDF is not 5. When you call IDF, it returns 5. So for any of these questions, if you want like few seconds to think about it, I'll be happy to do so. Just think about how it might be implemented. So here is a very verbose kind of way to implement it. Callable, right? Okay, I'll just throw in a class which has an operator, function call operator. Why not, right? Identity f, auto x, same old story here. Inner class has an x, has a constructor inner. It assigns whatever I to x, and operator that returns x, right? Let me give you a second, to or maybe a few seconds to look at it and just convince yourself that it actually does what the problem asks you to do. Meanwhile, I can have a sip.
It does what you want as long as the type of the thing you're calling with.
That's right. So Arthur is clearly awake. So what Arthur just said is, it's not entirely accurate, and that's because the inner class has only int state in it. But we have said, well, it's auto x, can be anything other than it as well. And if it's something really weird type, this is not going to work. So inner x. So by the way, the class inner is essentially just a declaration, right? I mean, a definition. I don't know, so right word. But this is the only thing that gets executed here. When you call identity f, only thing that gets executed, with 5 is this line. is essentially a constructor and it's returned. The object is returned. So if the new object called inner has 5 in it, and just return it. And this, because IDF is essentially of type inner, when you call it, this function will be called, and it takes no arguments, and it simply returns its state, whatever it has captured, and that's it.
Good. Unrelated question? Sorry?
The parentheses are.
Yeah, the const after operator paren, is that actually in a legal location?
No, it is not. Good catch.
Okay.
It is not. It has. I think it should be.
Operator paren.
Yeah, that's what I
Yeah.
expected.
Yeah, that's what happens when you code in PowerPoint. Yeah. So yeah, never code in PowerPoint. Yeah, thank you. That's good. So convinced that IDF is actually a callable that prints 5 or returns 5. Well, let's use a closure. So let's recall what we did. We essentially created a function object with state. It remembered one thing, which was x, which was passed as an argument to constructor, to inner, and it returned that object. So it remembered one thing, so it has clearly had state, and it was itself a callable thing. So we could perhaps return a lambda, but we really have to remember x, like how are we going to do that? Because we don't want to pass x here, because we are not calling the lambda. We have to simulate essentially the construction of inner, not calling. So, well, that's pretty simple. You just use, one of those. In an assignment here which says, well, whatever I'm using in the body of lambda, capture it by value. So it looks at x, says, okay, I see an x in my environment, my closest x, as I start walking up the tree or whatever, and I see an x here, and okay, I make a copy of it, and that's it. So this is essentially capture by value. Scott Meyer says this should not be done. I mean, in a sense that default capture should be avoided, but it's okay for our purpose here, because it's really not much of code anyways. Alternatively, you could have just said x, and it means the same thing, just capture x, that's it, by value. But key thing to remember here is not that you are just, it says simply syntax sugar, but this expression is kind of looking at what's around it. It's looking what it's using and tries to find where it can find that argument or whatever, and it remembers it. This is essentially what closure really means. It closes over some environment. That's why this special term really. What does a closure really mean? So that's that. And with this piece of code, you can do the same thing as before, and you don't even have to name it, because both of them are lambdas. It is some class singular inner, but you don't care what the name is, and when you call it, it's gonna print 5. At least return 5. So I'm convinced that this is actually will do it.
Well, at this point, I would like to pose the puzzle also to the audience of what are some cases where this fails, where IdentityF doesn't actually do what you want it to do.
As a very, very junior person, is the lifetime of the things inside of X could screw it up, right? So you get X by value, but if that value contains things which have lifetimes that escape where you create it, then you're in danger.
It's not copyable.
Yeah.
I was thinking of not copyable. Joe, your point was if X is something where its value contains pointers.
Yeah, things that are in. You can see how on C++ I am that. In fact, people have already been proved against that. But the things that are copyable but shouldn't be, which is not as good as things that aren't copyable.
Some things just aren't allowed to be copied.
Yeah, but if X was a unique pointer, this would not work.
Or a thread,
You know,
so, yeah, yeah.
Well,
Container.
yeah, this current
Should be.
code won't work in case of non-copy or say unique pointer. But there is a way to make it work, right? It is, you can use unique capture or some other things in C++14 and some tricks to do that. One way or the other, there is a way to capture the environment you are in. You can always write a lambda that can capture a state that you are interested in, or whatever it is using. If X happens to be a unique pointer, well, you'll have to do some magic over here. I mean, not magic, you just use a different
well,
syntax
in
to capture it.
C++14, you have that magic available. In C++11, I do think that you are stuck and you have to go back to using your class.
Perhaps,
Yes.
yeah, a class or bind
Oh.
maybe, stood bind.
Yeah. Then you could use FinA on there, and then you could get some issues of this, for this specialized class, and for this specialized class, I can do certain things. I wouldn't do this kind of operation, I do that kind of operation.
Well, the trick that you have to use here is for things that aren't copyable. You can't capture them by copy. You have to capture them by move. And there's no syntax for capture by move. Right? You have copy and you have reference, and that's it.
Well, but the FinA would give me the ability with the specification on there, because it won't compile. It'll go to the other option, and where I said, oh, this one is movable, and therefore I can do this. I can do that operation.
But how do you do it though?
I don't know. I'd have to. It would take you more than a couple minutes to write that down.
You could do something with enable.
At that point, you
Oh, that's what I mean, spin it, yes, enable it. Enable that. that's
But
right.
the spinning is not the hard part. The hard part is how you move something into a lambda. And in C++14, you do it within a capture. But in
Oh, I see. I didn't get
I-
too much. I thought, yeah.
Yeah, you'd have to do a non-lambda or
Yeah.
some bind.
Yeah.
Function object too.
Yeah.
yeah, you can just write your own or produce one using stood bind. I mean, both are actually discussed in Scott's book. So, I'm not going to repeat that here, but yeah, that's a good observation.
So I have a different puzzle or
Sure.
thing to think about, which maybe you're going to get to later,
Mhm.
which is what would happen here if you didn't have that equal sign there? You just had empty brackets.
I don't think it's going to compile. You need at least, you have to say what you want to do with the state here. Or whatever you're using here, you have to say something about it. You could say,
Oh, I might be
Value,
missing it. Sorry, I
no.
thought, isn't default capture, is it default to no capture, not default to capture by reference?
It is default to no capture at all.
yeah.
Okay,
Now,
so then I'm
you
thinking
really
of what
wanna
happens
make
if you
it-
put an ampersand there.
Well,
Yeah,
if
right.
you really want to make it a puzzle, what happens if you have an int exit global scope and you don't capture anything? I don't actually know the answer to that one. I'd have to try it
I
out.
don't either.
I think it
It
would
Well,
work.
do you want
works,
to
it works
have-
just fine. I did it today.
Do you mean like a global?
It's probably not going to capture anything.
Because I do have some global
Yeah.
struct defined, so
Yeah,
yes,
I can-
it did just fine.
That would compile, but not do what you would expect.
Yeah,
for sure. Because
Yeah.
the global is,
They might be smart enough to reject it somehow.
I believe it worked. That was Microsoft Visual Studio 13, so.
That might be
So
a
it-
There are no
undefined
rules
compiler.
applied, right?
you want to try
It
this.
compiles without.
Yeah, definitely. You know,
In GCC compile.
Interesting.
Yeah.
And if you
If
put
I,
the equals
Like
there,
all of those
Without the
cases are-
equals, you compile.
all of those cases
without
are, I think,
equals,
because
because
it
why?
was-
Yeah.
if you
Without,
have
without
X
equals,
available.
a global variable, it compiles.
Okay.
That variable
That
says
makes
that
sense.
it's,
Yeah.
I can
It
tell
has
you
to
exactly
capture.
the message.
The
that
global
it
variables
says.
don't actually get captured.
Right, you're using GCC with Xcode?
Yeah.
Interesting.
So its variable x cannot be implicitly captured in a lambda,
Would-
whatever.
And I guess
Is
static
that
variables are
GCC?
also
Is that
you know,
GCC?
always in the scope.
Ah, yeah.
so-
Okay. Important to know the compiler, right?
Lambda with no capture default is specified. But for the
So
global-
for globals, without anything in between here, it works, combines. It just
For
finds
global-
X somewhere.
Without the equal sign,
Global.
it captures a global?
Yeah.
Mhm.
It doesn't capture the global, it just uses the global.
Just-
Just uses it because the global is always in scope.
It doesn't
globals are
capture,
global.
that's.
I thought
that's
it did no
correct.
So it will-
capture,
it
it
will
did no capture.
return different
But
values.
It
it's
doesn't
not-
do an
it's not
capture,
captured,
but now
it's
you have
just-
a function which references a global variable.
Yeah.
So
So
you have to-
X is in
the
scope,
row scope
so
is what?
okay.
Okay.
So
Mhm.
capture and scope are two different things.
You capture things that you need to actually hang on to by copy or by reference, actually have in your function object.
Right, something
Things
that
like
makes a
globals and
state.
statics, you don't, or references to
Yeah,
other
okay.
functions, like you know where they are. You don't need
Right.
to capture anything that points to them, you already know where they
It makes sense, right? You
Very
could use some
easy.
function there too, that it's in the scope, so it makes sense.
Okay, so let's
Put on the
let's
cover
continue
here.
here, and
You're
okay,
gonna
we
get
learned
fired.
interesting things, but again, we are not going to use any globals or statics, and no surprising things. We don't want to, think about things that are not in the slides. Like, okay, global is over here, and it's just somehow got.
I wanted to, can I jazz off a little bit here? So, okay, I want to pass in it by reference.
Over here,
No, auto reference.
okay,
And then I want to put an equal sign there in the capture. I can't put a reference, right? Because it wouldn't
That-
work with the reference. I think it won't work with, if you put a reference with equal sign.
that should be okay, because, well, this particular code is probably not going to work, but essentially what you're saying is X is a reference to something, and as long as you have an assignment here, it's going to make a copy of whatever X is referring to. So this inner lambda doesn't matter, how you are capturing it, not captured.
I think it'll remove the
Passing.
reference automatically. It's like what auto would do if you declared a variable, like auto y equals x.
Yes.
That will still, the auto will pick, int not intref as its type. And I think that the lambda capture by value does the same thing.
Okay,
Yes.
but I couldn't put a reference where the equal sign is, right? I don't think it would work.
Well,
Equal
I mean,
and-
it would do something, it
Uh,
would compile.
It would compile and then you would have a dangling reference. Because that would then.
I'm capturing a reference by a reference?
Well,
Does it?
Well,
when you
dangling
run-
reference is up to, if whatever X is looking at,
It's a double reference?
if it outlives the
No,
the
references
lambda
overlaps.
or the closure, then you don't have a dangling reference. So you have to make sure that the closure that's written here does not outlive whatever X is looking at, in case of a reference. If it does that, then you have a dangling reference, but you could always just call down the stack and make sure when you go back, you no longer, you lose that reference, you get rid of it essentially some way. So you can always pass down because it is always going to be in scope, right, in your stack. So,
I thought I had a compiler problem when I put a reference there, when I passed the reference.
It doesn't break the program, but
I would expect reference collapsing to happen.
Well, it's not really reference collapsing. Reference collapsing is where you have an L value reference to an L value reference, and that gives me an L value reference. But in this case, it's really just the semantics of reference by itself. When I say X in my program, and X happens, the variable X is really a reference to something, and I say
Yeah,
X,
you can
I'm not
pass-
really talking about the reference
Yeah.
X. I'm talking about the referred to thing.
That's like saying you can't call a function that has a reference parameter from a function that had a reference parameter to it. Which you can do, which is exactly what you're doing
Yeah,
now.
it may be more a matter of.
yeah, you have to
recollection.
always remember, it essentially turns into something like this. And whatever you can do in a constructor, you can always have a reference member, or this can be a reference, this can be a reference.
Yeah.
So whatever rules apply there are applicable here.
Okay.
So, yeah. There's a lot to remember because you don't see the code right in front of your eyes, but yeah. So that's why Scott goes into some guidelines about how to use.
although that you can,
captures.
in that class, you could do a reference, that doesn't mean that it's correct, right? Because you're referencing a variable that it's from that local scope, right?
Well, it depends on where identity F is called from, right? If there is a function here, and I could replace all these with references, and still it's going to be fine. And
Then
it is-
5 will be okay.
because you are still in the scope, and this whatever thing that you're passing in as a reference is still in scope. So you call IDF, okay, return whatever it did, and then it's fine.
Well-
So, but if you return IDF outside this, now you have a damning.
I'm not sure if that's true in the case of identity f of 5, because when you call identity f, that's going to push 5 on the stack, not pass a reference to an existing 5. So
Right,
then
the reference
that
being
stack is going to be
captured by
immediately
this
popped,
lambda.
and you have a dangling reference.
No, I'm not even sure if phi is a valid argument because maybe
No,
it's
well,
like maybe I
it
will
is.
assign a argument and then pass phi because this is gonna be a R value and maybe some bind with auto reference at least. It may bind with auto ref, but maybe not auto ref. But I have to really check.
It should bind the auto ref and it should deduce the auto part, the T there should deduce this constant.
Oh yeah, that's right.
However, so you're
That's
saying you're gonna
possible.
do auto ref and then you're gonna also capture it by reference.
Yeah, that was what I was really thinking was gonna be a problem. I don't think it's gonna.
So the
I
five,
think that would
that
compile,
value
but then it
five
wouldn't
there
work
is
in
gonna
this.
live until the end of that expression. But then on the next line, the next expression, you're actually trying to call IDF and you reference that
Oh, but oy vey.
captured reference. That's not gonna
Yeah.
work.
Yeah.
But it's totally fine as long as you never call it.
Yeah.
It's just not okay to call it.
Yeah, what I was referring to was, if you, when it's a reference, I don't want to pass just phi. I would create a variable before this, call it foo, whatever, assign it phi, it's an integer, then pass that one. So now, clearly, as long as that variable, which you don't see here about this line, exists, any number of calls to IDF are okay. But if it works like Arthur says, which I think it does, which is okay, a temporary or whatever of 5 and then, I don't know, this is maybe UB line. Okay, ready for the next one? Okay, so just a recap, lambdas and closures, make sure the difference is clear. Lambda is essentially syntax. It is what you really write in the C++ source code. A closure is what exists at runtime, which is an instance. It's the same relationship as class and object. Class exists in source, objects exist in runtime. And closure, closes over. It may have state. And what else? In most, in many other languages that have closures, they automatically sort of extend the life of whatever it is capturing. So, for instance, in Java, at least Java 8 or JavaScript, I guess. But here, if you want to do that, you have to sort of use shared pointer because a shared pointer is the only way to sort of you have something. When you make a copy of shared pointer, of course, you have an additional reference which is counted, and it won't go out of scope as long as you have at least one reference. So this behavior is not there, or I should say it's only there when you capture shared pointer. Otherwise, if you capture by reference, like we discussed earlier, it's gonna vaporize in thin air somewhere. Depends on your program, of course. Any questions on the difference between these two? Okay, I think now it's going to take a little more, well, maybe after this. So let's look at the state, right? I mean, let's do some meaningful modifications to the state. So let's write a function that produces a function that returns values in a range. So that range being 0 to 10, let's say 0 to 9, 10 being past range. So let me give you a few seconds to think about how you might write a function that does that.
You mean the generator?
Something like that, yeah.
Oh, you mean return a random value in that range?
No.
Or return
No.
Do you mean
Right,
return?
so it's more
every time you
iterator
call
type,
it, it returns the next value in the range?
Yeah, maybe it's not specified clearly here. So you read, okay.
That's
The
for
idea
sure
is to
range two.
return something from 2, and that thing when you call one up, successively up to 10 times, it should produce 0, 1, 2, 3, 4, 5, up to 9.
And then what does it do after that?
Up to you. UB is valid.
Well, then you don't really need the upper bound, do you?
Yeah.
That's right.
At that point.
So it's going
But
to
the idea
use
is to
the
really,
usual state.
stop, at 9. Okay. Let's see. So from 2, right? Whatever it returns is a range that goes, when you call range, say 0 to 9 10 times, it should produce those numbers. So that's my lambda, start and finish. I have to return something which is itself a callable, a lambda. So return whatever follows is a lambda. By the way, that lambda needs to remember what from to was called with. It's like the range is given to you, right? It should return, it should take everything that it needs with it, because later on it needs to stop at whatever, 9. So it needs to remember start and finish. So we have capture by value, a default capture by value, and I'll come back to mutable in a second. So if start is less than finish, so this is, by the way, the inner lambda, right? When you call it, it's going to compare start and finish. It has already captured both of them because of that equal to sign there, and just return start plus plus. So as you call it successively, it's going to return 0, 1, 2, 3 up to 9, and when it exceeds that, it's just going to throw runtime exception. Just saying complete. So who can perhaps here explain me why mutable is there? Anyone who has seen this even before?
Because you need to change start, and by default, the things that are captured are going to be const. Which
That's right.
Is because the operator paren is itself a const method by default.
All right. Yes. Thank you. So that's correct. So this function call operator that is produced by the compiler, by default it is const. So it's trying to save you from modifications. It's like, okay, let me just slap on a const for you, because if you really want to make modifications, you need to tell me back by mutable. So now it will take out the const. There was just a while back a question about where the const belongs, right? So that const will be essentially gone. It was incorrectly placed, but that const will be gone. And this particular lambda, the closure object, its function call operator is non-const, so it can change its state. It can change start, it can change finish. We are only changing one here. Does that make sense? How we could perhaps create a generator that given a range, you can now use from many places. You can just pass in whole bunch of ranges, like 0 to 10, 10 to 20, whatever, doesn't matter. Each time you're going to get a function. Now think about it. You are producing functions that have different behaviors depending upon how you call this outer thing. Now you're probably starting to see how powerful it can get, because from to whatever at runtime it's just producing ranges, just throwing at you ranges, whatever you're calling it with. Okay. So no questions. Let's go ahead. All right. I think I've been waiting for this slide to come up. So write a function that adds from 2 invocations. So that's valid, by the way. You can write code that actually does that in C++. In fact, I'm right now asking you to write such horrible code. But it's fun. It's fun because it's really interesting. I'll come to it. What it has even name for it. So when you get that. So add f. Let me explain you what this thing is really doing. So add f is a callable, a function or a lambda, whatever. You call it once with one argument, 5. It produces something that itself is callable. We saw that earlier, right? We just split it into 2 different lines. Now I'm putting in the same line. The second call is right after it. You have actually seen this code before. So whatever add 5 returns, you call that with 4. And as a result, it should produce 9. Clearly, it's doing some addition somewhere. Again, take some time to think about how that might be done. And believe me, this is a useful exercise. At least to me. And function programming. Before seeing the answer, anybody want to give it a shot perhaps what we might do, or just want to go right to the answer? Okay. All right. So I will give another 30 seconds to convince that this actually does what we just said.
Sure.
5 lines of code, almost 3. We maybe never thought like 3 lines of code could be I don't know what's the right word. Mind bending, I guess. So, okay, let's go through it. So add f, outer one. Let's not look at this at all. Let's just see. Hey, the outer one is just straightforward. A lambda that takes an x. That's it. Single argument. It has to do something with it. Well, it has to, of course, return something that is callable. So return a lambda. So we got up to that. We started returning a lambda. So the way I wrote this, I did not write this in the order you see it. It is in fact you have to sort of go in from outside. I don't know. It's like, so I wrote this part first, these 2 lines. Add f a lambda that completes. I know that's it. So line number 1 and 5. Then looking at this, its use, I see that okay, I have to return something that's callable. So I have to return a lambda. So let's start writing a lambda. So that's these two lines, number 2 and 4, and I wrote that. Clearly, it's taking 2 different arguments. One is x, one is y. And now, when that one is called, it has to do what it's supposed to return. 9. Essentially, do the right thing. It adds at the very end. It's like, okay, I'm just gonna scoop up whatever I'm gonna get. And I'm going to do the final stuff, the addition, the real work at the very end when I have got everything that I need. So clearly for an addition here, I need at least 2 arguments, x and y. But by the time I call add f, I just got x. It's like I just got half of my x, half of my expression. I have to wait till I get the second piece. How do I really wait for it? Well, you could return another lambda that when you pass the other half, which is y, now you have x and y that you need to do finish this addition. And that's how we end up with 9. Does this make sense? It's kind of twisted, isn't it? Why would one do that? Why not just pass 5 and 4 as one argument? I mean, not one argument. 2 arguments to the same function. You can always do multiple arguments. So why like constrain ourselves with the single argument things? And we'll look at it. This is kind of a very powerful thing to do. So does it make sense? Yeah.
Are you getting to currying?
Don't take my thunder away here, whatever it is. But yes, it is essentially currying. That's right. And what's happening here is currying is a way of splitting a function that takes multiple arguments into one argument at a time. So you can do interesting things. I think let's just say that. And it is essentially doing currying in a very I don't know, I guess a very manual sort of way. You're writing code to do each step one at a time. This is what a good functional language compiler, functional language will do out of the box for you. It's like no questions asked. It's like add f is a function which takes 2 arguments. You pass in 5, just 1. You're not giving it whatever. It takes whatever n arguments. You're giving fewer than n. it's happy. It doesn't complain. It said, okay, I will give you a function back that you have that takes the remaining arguments essentially. Well, strictly speaking, in currying, it takes exactly one argument. So if we were to do 3 arguments here, 5, 4, and whatever, one more after this, you could see that even the third return will be another lambda, which will take the third argument. So the longer this expression gets, deeper the lambdas get, which is really weird, but I think it helps drive the point that when you return, you can return functionality, which is, and half of which is kind of bound, it's kind of partially applied, if you have heard about that term. X, it's the whole functionality 9 that produces addition. You're bound 5, so it's like you will always add 5 to whatever you pass in. So if you have something that adds 5 to anything, just pass this guy, because it knows what to add in the last piece. Whenever it gets the last piece, you just add it. But something to note here is, look how x plus y, the innermost expression, is actually referring to its captures, even outside, as you walk out. It takes a bit of, at least staring at code, that this particular lambda captures x, which is argument of this.
Right, I think that if you wanted to make a function that added 3 or 4 or 5 numbers, you might start thinking, oh, this is going to get complicated. How do I curry this thing? When the outer level I have to remember the first one, on the second level I have to remember the first and second one. This is getting complicated. How do I write this? And it turns out the syntax is just exactly this. Just nest that second line there, return bracket equals bracket, auto the next argument. You just nest those, and at the very inner portion you say just return x plus y plus z, and it just works. Takes sort of the mystery out of currying.
That's right, yeah. I mean, currying actually feels weird when you think about it without any construct like this, that we are familiar with. When you know currying, or you come from math background, that perhaps comes naturally without even looking at syntax like this. But with this, at least it helps me. Hey, it's essentially a function, and we look at that. How we're just passing one argument at a time. In Haskell code, this is exactly what actually sort of happens, because it's happy if you do just one argument. The rest of it is taken care of in the same fashion. Okay, so how much time is left?
I don't know.
About
Until like 9.
till 9? It's just 8, 9. Okay, so how about a function swap that swaps the arguments of a binary function? So swap takes, if you remember, sub was a lambda defined earlier at the very beginning. It takes that one and produces something that will do the same thing, right? But of course by swapping the arguments. So now you're sort of putting things together. You have this little bit of functionality called subtract, but you don't. Now you're building this swap functionality that's reusable. Right? You could perhaps replace this with add or mo or whatever. For mo and add won't make any difference because swapping doesn't change much, anything actually. But that's why sub. But you could see that you could write a function called swap, which is sort of generic, not in terms of just values, but in terms of its behavior. So let's jump into code. So subtract again from the first few slides, same as before, return x minus y, pretty simple. But swap now takes a binary function. Again, it's auto. You don't care what the type really is. It's just auto. Compiler will find out, figure it out. You don't have to worry about that. And again, if you want to write this code yourself or pass it right now, start looking at, go from outside edges to inside. That will make a lot more sense. That I have a swap x function, and then I return another lambda, that's why line 2 and 4. And once again, you have to capture whatever you are going to need later on, right? You return in here binary yx. So this is where it actually did swapping. So it has to capture, this inner lambda has to capture binary, and x and y will be passed in as arguments. So okay, write a function that takes a binary function and makes it callable with 2 invocations. So it's very similar to the earlier one. The earlier one was just using add as its functionality, but here we have to produce a function that makes any function callable like this. I think this sort of exercise helps that what state you might have to capture in a lambda, and it's amazing that lambdas can do that. When you start nesting them inside one another, it becomes really weirdly powerful. And you will see at least in some libraries, like in C#, where lambdas have been there for, I don't know, 8-10 years maybe, it's very common to see 3 or 4 nested lambdas just like that. And then to really understand that code, that's how I started it. When I looked at the conference, I think it was in Redmond, Washington. It's like 3 or 4 levels of, I was asking my the colleague next to me, like, are there 5 lambdas in this code? And he looks up for a second. There are 7. Why are you counting? And it's like, hold on, because it's like I'm just lost in counting lambdas. Like, where is it and what is it doing? But that's the kind of style you might think is not going to come in C++, but just wait for a minute, not a minute, a few years. Give some really smart people enough time, and you will see some really crazy libraries that will start making use of this. Actually, a library like that exists already, which is more used in Java and C#, which is Rx, which I have been using. Pretty fascinating stuff where it's just second nature. It's kind of, you just keep doing that all the time. You just produce functions, pass functions. When you have functionality like Lambda, it's not just about one level of confidence stood algorithms. It's coming up with libraries that can make use of designs that can look at that may look something like this. The building blocks here are going to be useful to build really different sort of designs and libraries and perhaps understand how they work. And that's why I think it's kind of useful. Okay, so it is again very similar. You probably got the idea already now, like what's the pattern here. 3 arguments, right? I mean, essentially 3 successive invocations. So we are going to return 3 lambdas whichever way. So auto binary, return another lambda x and y, take x, take y, one at a time, and then at the end of it, when you have got everything that you need, your operation and all these arguments, then actually perform the operation. So one way to think about this is the way these lambdas are executed, or the compiler, the runtime program goes through this, is actually in reverse order of these closing braces. I think that was the interesting suggestion that I was given, that when you run apply f with mul, it runs this and it just returns something and that's it. It ends here. It does not go through this. It is to be done later. It says, here is some computation I will do later on, call me with the right things. Okay, next thing, 3. Now it enters here, it returns something and hits this closing brace. And that's that. And at the end, it's 4, it enters this one and does what it does. So, although the code looks like this, it's executed at runtime in sort of lazy fashion. I think that's the way to think about it. It's sort of lazy. It doesn't want to do everything in one shot. It just it's going to keep pushing out whatever it wants to do. And it turns out to be a really powerful concept to create interesting libraries. Okay, so someone already mentioned currying. So this is essentially currying, and I'm using that term here, currying mul3. We're taking 2 arguments here. Again, very similar one. I don't know why I have this particular example, just to introduce the term curry essentially. If you don't have, if you just take 2 arguments at a time, then the lambdas become smaller because there are fewer lambdas because you don't have to pass in as many times and nesting levels of the lambda.
And you can also implement this one as just return apply f of binary of x. Right? I mean, we did that on the last slide.
Apply f of
That is curry of mul comma 3 is the same thing as mul of 3. Or sorry, apply f of mul of 3.
That's right. It is essentially the same as this piece. Yeah, this on the left hand side of it. Yeah. Okay, so Kareem and whoever can pronounce that. So it's a technique of transforming functions that take multiple arguments, and you can change those functions with single argument. So if you want to understand Haskell, here is your, as promised, Haskell code. If you want to understand Haskell, even the simplest function declaration in Haskell, you have to understand currying, because that is exactly what it's doing. So it's abundant, you can find a whole bunch of examples online, of course. Something like that, as weird as that, like A arrow, right? It's like does something in Haskell. Well, it's actually that line here is actually a signature, essentially a type for function max, like std max. And let's not look at ORD just yet. It basically says any number, something that can be ordered. You can think of it as, you can just think of it as int for now. But Haskellers are going to kill me right after I step out if I call this int. But anyway, I'll take that chance. So we are saying, well, max is a function, and it takes, well, how many arguments? Like, what is this? A arrow, A. But it is exactly same as before. It takes 1 argument actually, the first of max, the left argument for max, and returns a function that takes A, another A. Now you've got 2 things to compare with, max, and it returns 1. That is exactly what we did. How you might write max as one argument at a time. You return a function, a lambda, that will take the second argument, and at the end of it will compute. So this is essentially a shorthand for that. A function that takes A, this essentially is a function, right? It takes something and produces something. In Haskell, in functional languages, you always take one, not always, but you take 1 argument and you produce something. So always like going from one place to another place. So you take something and you produce a function, and this is essentially a really tough syntax to say, what we already looked at. And now you pass A, and that's it. So here are some other examples, less than, greater than, and others. So there you have it. With this, you could start parsing Haskell code. I think, because it took me a while to figure this out. It's like, what does this really mean? And after going through Douglas Cox's talk, I could start sort of appreciating what is happening. And then it goes way out there from here, pretty amazing stuff. Any questions on currying at all? And
well, I've got one more puzzle. Speaking of the
but there are plenty after this, but anyway, let's go ahead.
well, maybe I shouldn't then. But the apply function took a 2-argument function and returned a curried version of it. And you can imagine writing one that would take an n-argument function and return a curried version of it. Or can you? Is it possible to write in an arbitrary, please curry this function that will take an arbitrary callable, no matter the number of arguments, and give you back a curried version of it?
With variadic functions can do that?
Well,
You would
Can
need that.
the
I'm
catch
not
is
sure if it's
you
enough.
don't want to go there because variadic is about passing in whole bunch of arguments at a
Yes.
time. You want to pass exactly one at a time. It's
No,
like-
but there's a size n.
There's a trick to this question.
Yes.
And you would have to take something that takes at least 2 arguments. Because you would start with like something that takes 1 argument and then some more arguments.
Mhm.
And then you curry the first one and then pass some more arguments to yourself, which might mean that you can't do this with a lambda. You'd have to do at least the outer level thing as a name function.
Well, so what would the idea is if I say curry of add, I get something where I can then say that x, y, but if I say curry of add 3, then I can say that thing x, y, z.
Well, we just pick max and make max be an arbitrary number, right? Max of 17 different numbers or 37 different numbers. And it goes through the whole list and figures out the max, right? Is that what you're asking, sort of?
You just keep carrying each one that you get returned.
No, but you want to make it general, so
Yeah.
I don't know how to make it general. I don't know.
Right.
So
So,
if
well,
you-
what would it return if I just gave it a unary function, like curry of negate?
Well, unary function would supposed to return the value, unless you want to return a function. But then how do you know
You do,
you
you
jumped
wanna
off
return a curry.
the end? How do you know to stop? I guess.
Sure.
You
Like
need your
curry
base
version of
case,
negate.
which
Yeah.
means which you could do with overloading.
Well, what is curry of negate? It has a value that can be expressed in words.
Negate, I think.
Right.
Just written itself.
Right. So I think you couldn't define that version of curry with a lambda because you need kind of 2 definitions for your base case and your approved case. Or is there a way
You
to
can
do it
still
with
do
lambda?
that with the lambda because you can capture state and like curry 3 can decrement 3, and when you get 0 you return the final operation, and in between you return, like if your state is less, you return the lambda.
But that would be like an if statement at runtime. You need to return 2 different types. And that's,
Yeah, you can return it all the time, so.
Yeah,
you have to
So-
make that
but it's
statement at
auto.
runtime.
It should be able to deduce that.
Well, no, it can't be
Maybe.
2 different.
Auto has to be
types.
deducible at
You're right.
compile time.
Yeah.
It has to be same return type for both return statements.
I don't know. Can you do this with a single lambda?
Can you do this at all is the question.
I don't think you can do it.
Well, you can do it in a different language.
Yeah.
I think
You
you
do it
can
in
do
list.
it with a handwritten function object. I'm not sure if you can do it with I could be
You
wrong.
actually can't because let's take what is curry of max. Like, what's the obvious way to define max? It's not as a 2-argument function. It's as a template that takes, you don't know how many arguments, right? You can say max of A comma B or max of A comma B comma C comma D.
Well, that's the size dot dot dot.
How could you
thing.
return a curry of max? Right?
Oh, but it
if I say
calls it
max,
some-
if I say
Oh.
curried max of A of B,
Okay,
what does that give you?
You're
It's
asking
giving
for
you a bigger
something more
dimension.
general than I thought.
Right?
So isn't that the size dot 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 thing and you call itself until it goes down to 0, right? That's how you do addition of.
But that means you started with a variadic template somewhere, which is going to take more than one argument.
You have types.
But that's
doesn't work.
we don't want that. We
I
don't.
think
We
you can-
never want more than one argument when we do curry. It should always say exactly one.
I think you can.
The
correct me
trick
if
is
I'm
that
wrong. I think
you
you can do a
can-
curry that takes any function with a fixed number of arguments n, but you can't do a curry that
Mhm.
takes
I
a
think
function
that-
which
I think
itself
that's-
doesn't have a fixed number of arguments.
Right. Where that takes because what is a function? It's a
Because a
value.
template is
value,
not a
it's an
function.
object
Mhm.
that can be called with operator for n with some stuff. Unfortunately, there's no way, given that value, to figure out what is it safe to call operator for n with, right? What is the arity of this function? The answer is quite often it has multiple arities depending on how it's defined. Right? You can have an operator for n that takes a single int, and another operator for n that takes 2 doubles. another operator for end that takes an arbitrary number of.
I was thinking
So-
of doing it with a function pointer, or with a standard function where the arity is defined. You can't actually do it with an arbitrary function object.
By the way, in JavaScript, you can do that. I mean, it's a completely different story. It's very
Because
dynamic.
you can count your arguments, that's not fair.
It's
But,
just set arguments as an array.
You
I
can
think somebody
do it
suggested here as
separately as well.
a array or vector or something like that. But yeah, that's how it does it. It's still not first class in the language, but there are workarounds to really make it. So yeah, that's why it's really more.
So you're saying this is possible?
No, I'm saying it's not possible.
Well,
That's
okay,
the trick.
is it a problem because you basically have to return two different types?
The problem is basically that you don't know when to stop currying and actually do the work, unless you know how many arguments your original function took. And your original function might be a template that can take any number of arguments. Or it might work with one.
I could see an answer if you said you keep on returning and returning the function, like if you want to do add, and you keep on putting 5, 4, 3, 17, 19 in there, and until you get to the point where you say open and close paren, which is empty. And then
you
you say
need
it's your
terminal.
interval.
Sure, but that's not.
But the problem is the return
Yeah, it's
value is
not quite
different.
curried.
The return value is different. Well, I mean, but I
Well, bottom should be the same, like the bottom type. Should be the same.
Well,
type.
with the bottom types, I'm returning the sum, which is whatever number, and the other times I'm returning a function. So
Okay, yeah.
I just don't, yeah, so, I don't say you can get there from here, but maybe, maybe in 22. Visual Studio or Microsoft C++ 22 or 21, whatever they're adding up number to that, right? Are there plans to do this? I guess, are you leading us on it?
I don't know. This.
No, I mean,
Well, the answer I was thinking of was it's not possible.
Yeah, but is the committee have any idea that they want to do this then?
I don't think it's possible.
It is if you don't have types.
You
but
have to
that's
make
really-
C++ a completely new
Because-
language. It is already
Yeah.
looks like a
It's
new
incompatible
language.
with
Because you
now.
can certainly do that in
static type or,
Scheme or Lisp
not
because you
Lisp.
don't really have strict typing, and you can do exactly what I said of keeping your arguments and returning stuff until you no longer have a counter.
Where do you get this counter from?
It's like curry 3-argument thing, and it'll make a 3-argument courier. But you can do because you can do that in Lisp because it doesn't have types the same way.
By the way,
So
in
you
Haskell,
can ask-
it's all statically typed. So whatever that means, I don't know much how it does it, but it knows exactly how many arguments it takes, and it's going to compare that with your use and say, think about it. If you pass in more or less,
The-
more
Haskell,
arguments
everything's
actually.
carried by default.
It is correct by
Yeah.
default,
Yeah.
always.
It's
It's correct.
easy.
I was thinking of asking the question, can you do this in Haskell, but it's meaningless in Haskell.
Yes,
Everything's
sounds
already
weird.
curried.
Right.
You can't do an uncurried function in Haskell.
Okay, actually, you know what, from this point, I mean, we could stop anytime, actually. Other examples, many examples are just variants of, the same idea, but I really wanted to get up to currying, and that's really the point I want to drive. It's like one small concept in functional programming, which is now possible within certain limits in C++. If you run across certain, most of the times, you know how many arguments you're going to take, those kind of things. You could still apply this to design a functional library. Something to keep in mind. Okay, so a related concept, partial function application. This is somewhat different. It's like reverse of currying, but you're doing more. You're taking more than one argument at a time. So you remember more than 2 arguments. So let's say add 4 is a very simple function that takes 4 arguments and just adds them together. That's it. A partially applied function would be something that captures, let's say, 2 arguments or 3 arguments or something like that. Not 1, because if it's just 1, then you're back to currying. But if it's like 2 arguments, then that's what this one does. Take A and B. So it took 1 and 2 for add 4. So now whatever it returns, it's like, okay, I know my 2 things, so I'll save those with me, essentially some state. And give me whatever the remaining 2 later on. And that's what it does. So a fine difference between two. Sometimes comes up in if you read about things. These two things can be a bit confusing, but essentially, partial function applications like at least two things that you have to sort of. If it's just two argument function, then you cannot really do partial application because it's like one argument, just currying. Okay, so create a function. Okay, three ways to create inc function, but for this really, it's designed. If you are working with code already, if you have something to look at in your laptop or what have you. So three different ways. Let's look at them anyway. So someone already suggested, you could just do curry add 1. So if you remember, curry essentially takes a function that's binary and fixes one argument. That's increment by 1, right? This increment will always add 1 to whatever you pass in. This is another one, add f1 and apply f add 1. They are all the same thing. They're doing the same thing essentially. It helped me quite a bit when I went through this exercise and wrote code. It's like, okay, how can I do this? It takes a while actually to start thinking in those terms. Returning functions is not usual. It's like regular C++ programmers. I know those who haven't done functional programming cannot becomes weird. This is I have this slide in here, but I dropped this. Anyway, another function. Compose view that takes two binary functions, two unary functions. So inc, we looked at it, it increments anything by 1, and returns a unary function that calls them both. So now this is something classic in when you start using Lambdas essential functional programming. You are just passing in behaviors. Maybe by this time you're not surprised to just see whole bunch of lambdas going inside functions and whole bunch of at least one of them coming out. It's just as common as sending in values, vectors, structs, and whatnot. When you can do that as easily, it's like, okay, that's essentially functional program tells you to do. So we are passing in actually two functions here, and this compose function takes them and puts them one after another, so it composes them together. I think it's easier to see the code than thinking about it here. So first function f1, another function f2, and it returns function that is supposed to apply both of these functions on this argument. So now you could think of some, maybe two behaviors. It's like, okay, the values keep changing. Let's say you are looking at, I don't know, some data coming off of a network, maybe. So you don't know what data is. So what you can perhaps do, but you know what needs to happen with each data. Each tweet, maybe you wanna split it into pieces and then, I don't know, count them or something like that. So what you could compose together is like functions called count, split and count, and leave the other stuff that keeps changing for the later. It's like, okay, I know what I'm going to do. I'm going to count them, I'm going to split them. So let me compose those together with these. And okay, split, you get an array or whatever, or vector, it's your choice. Pass that to count, and it just returns the number of words in your tweet. So now whatever you return, it's like whatever you return here, it becomes your new function, right? It's like new function that does completely different things than you started with. You started with two functions that one does count, another does split, splits this open thing, and then you get completely new functionality at runtime, by the way, by composing them. And you can compose third one if you want, but there's going to be different code. So you can think about, you don't write functions, you produce functions. And just like you produce values, right? You produce functions. Yeah?
I keep on getting 16.
Come again, 16, or about 16?
I get 16, not 20, so I must be doing it the wrong order.
Okay, let's go through this. Sorry, I probably
It's a left to right, right to left thing, I think.
Merv 5 should, whatever is passed here, which is F2, should multiply by 5. Okay, so actually I think you're right. No, it's F1. No, it's F1. No,
It's
it
a left
is-
to right, right to thing. Is it?
Yeah, the
Yeah,
int one.
F1 is applied first.
Yeah, F1 is the first function that is applied, right? To x. So what's F1 is inc. So
Okay.
Take 3, increment it.
Okay.
Yeah.
so
increment,
take
and
3
then-
increment
okay,
it,
yeah.
make it 4,
Then-
multiply it by 5.
This is the left to right left thing that they argue about incessantly in functional programming. Okay. The fold left, fold right stuff, right? Okay.
No, not
But
quite
is
that.
it
It's like
order guaranteed though? Is it order guaranteed?
Well, it's up how you write, right?
That's
I
how
mean,
you
you could
write,
you could
yeah.
swap this. It's up to you. I mean, it will be some completely different, right?
The
What it's
person
doing, it's trying to
defined
say here
compose.
is like, I will do this
This
first.
is using compose.
Then I
using
will do
from
this.
Right to left. I mean,
Perhaps something
traditionally how
else.
it's done.
I don't know what's traditional. It's like, whoever wrote this had to make a decision of
I know,
which
but
way
I
it
thought,
was gonna apply
I
them.
thought traditionally it was from right to left.
No,
I would say that traditionally-
it's just like you read
What?
from left to right.
The
Whatever is
compose
passed
is
here,
the,
Yeah.
Just do the first thing
Little circle is
over here.
Yeah.
F compose G of X is F of G of X.
Okay. Well, every example I've ever seen in JavaScript has always been from right to left, and they're very.
Don't use
consistent.
JavaScript as your gold standard.
Well, I mean, but it's still, but okay. Well, anyways, I mean, that's why I say it's more traditional that way. That's why I'm really confused.
Well,
I would
this
actually
one is
prefer
the
left to right. You know, I mean, the funny thing here is.
It's not right. It's just a matter of convention.
It's more than convention. It is what people would, I think, would prefer because you read left to right almost all languages. So I would really want to use, okay, whatever comes is your argument. I don't want to look at this, right? It's just data is coming at me. But I just want to look at this function and say, okay, it's going to do increment first and then multiply. That's my logic, you know. It's like maybe split. Okay, I want to do a split. It's like pipeline.
Mhm.
What is the operation that I want to happen on this as data comes in? Like, okay, split it, then count it, then maybe, mix it all caps and then do something. One after another. I don't care what data that is going to be. Just do these things left to right. In English, I would say, well, in left to right, right? I mean, and then I would really prefer it in that order. Now in C++, we get a luxury to overload operators. Imagine if we overload compose you sort of, not actually compose you, an overload operator, let's say the greater than, the right shift operator. We could in fact replace comma with greater than, and maybe something after this. It will look inc greater than, more greater than this. If you look at that code, it almost looks like your pipeline. You can imagine, so that's the way. When you look at the code, I want to see what it really means, right? As soon as I look at it. In this form, it's twisted. Okay. By the way, Arthur, if you feel free to stop me anytime. I'm gonna just continue these, and if you want to discuss as long as you want. I think I've used my 90 minutes, but I feel happy already because I've gone past some interesting stuff already. Sorry, this is about a function that takes a binary function and returns a function that takes 2 arguments and a callback. So it's going to do something with those arguments and let you know the answer as a callback. I'll give you a second to think about that.
So what if this translates straight into C++, right?
Yeah.
Write a function, takes a binary function, so it takes something,
Yep.
and returns a function with that takes 2 arguments, x, y, and a callback, so 3 arguments.
3 arguments, yeah.
And it invokes the 3rd argument of the
on the result of it. Yeah. Yeah. Once you start, you know, you grow up it, learn to grow up, you see how it needs to happen. So pretty simple at this point, actually. That's that, you know, give you a second to look at it. So, because this is a callback now, you can start doing interesting things. You can actually start passing in lambdas to the callback, because now that's how you get your answer back. You know, so let's look at the
Why
bottom
did you
line.
use int instead of auto?
I don't know. I don't know. Just maybe because I was doing addition or something.
Habit.
Yeah, I mean, yeah. Hopefully, I mean, at this point, it's like auto and int is like not the point here. Absolutely, it's the weird ways you can just compose these things and you know to produce interesting things. And of course, then you have to add decal type and standard forward and just add all the sequence complexity, universal references, move semantics, and happy coding with that. So, yeah, binary move. Okay, produces takes 3 arguments, 1, 2, and 3. The third argument being a callback, a function that you pass in. That's that. So it's gonna multiply 5 and 6, make it 30, and call back that. That's it. Any questions?
I guess we could stop at this point if you want.
Okay, sure. I mean, yeah, there are probably just a few more slides. Feel free to go through this presentation is up already. I would encourage you to go through each and code it before looking at the answer. Now you know most of the answers, but it's kind of interesting. And I guess it should really open up a really big chapter and a completely new way of thinking about programming. Right. Thank you. Thanks for listening.